Welcome back to Computer Science 4300. Today we are talking about, we're here on lecture 15. Wow, it's been 15 already, way more than halfway through the course. We're talking about pathfinding and steering. And so I've got some slides here. If you've done Computer Science 4303 with me, that is a course called Video Game AI, or AI for Games. And this is a lecture that's shared between the two courses. And the reason it's shared between the two courses is because you can't talk about game programming without talking about pathfinding. It's just, you need things to move around in the game, right? And you can't talk about game AI without talking about pathfinding either. It's like the most basic thing that you need in every game, and it's the most basic thing that you need in every AI system for a game. And so, you know, there's one lecture that just completely overlaps between the two courses, and I'm not ashamed of that because it just has to. So let's get into the lecture here, because I have jammed a bunch of information into these slides. And just keep in mind, for the context of this, is that in your project, you have to implement some sort of non-trivial pathfinding. So that doesn't mean you're going to need to implement A*, or you need to implement vector fields, or you need to implement influence maps, or you need to implement this or that. I just want you to take a stab at implementing some sort of pathfinding, which is more intelligent than just try and walk straight for the player, because it's, you know, that's not going to work the vast majority of the time. So we're going to go over a brief description of like movement in games, and also pathfinding and steering behavior. So movement in games. Movement, it's arguably the most important part of many video games, if not all video games. It allows the exploration of the game world and the interaction with the entities in the world. So not only does the player move in a game world, but the NPCs and the entities move as well, right? And good movement makes a good game. Who out there has played a game where like the story is great, the characters are great, the mechanics are cool, but like the movement is just so clunky? Like I've played so many games where I just, the movement felt like I was being restricted or smothered when I was playing the game. So good movement is key to a good game. So here are the main video game movement problems. The first one is pathfinding. So how do we get from point A to point B in the game? And whenever we talk about pathfinding, typically we're not necessarily talking about the player's movement, because usually the player, like if you consider Zelda, you are controlling Zelda, right? You are doing the pathfinding. But in some games, like for example, Diablo or Path of Exile, those type of games, when you click somewhere on the map, it's going to have to do some pathfinding to actually get you there. And also, enemies are trying to get to you, and so you've got to have pathfinding for that. Secondly is path following. So not only do you need to figure out the path that you should take, but how to actually move along that path once you find the path, right? There's also like the physics of the game world, so how the environment interacts. So do you bump into certain tiles and stuff? We've already talked about that in this course. And the animation as well. So how do your entities look while they're walking? That sort of thing. The animation side of thing is really important. However, this course isn't going to get too bogged down with animation. We've sort of said, here's how we implement animation, or a bitmapped animation system, and it's up to you to make the animations to fit your game. So in this course, this slide was taken from the other course. But in this course, or in this lecture, I guess, we're only dealing with pathfinding and path following. So let me just make a slide here. In this lecture, we will deal with, there we go. So in this lecture, we're dealing with decision-making for movement. So pathfinding and path following, not the physics or the animation. So here I have some examples of pathfinding, and I think the desktop audio is going to play. So here, this first example is from the Saints Row series. So hopefully this works. Okay. Wait, now. I got the laser pointer, so it's not letting me click. 1 second. Oh, this is so loud. So here we've got some pathfinding. I gotta turn off that music. Okay. So here we've got some pathfinding. Oh, it's so loud. Can't even hear myself. So you can see here that the pathfinding isn't necessarily the best here, right? We've got a drawbridge which is up, but the pathfinding, let me just play that again. You can obviously see that these NPCs and stuff are not considering the openness of this bridge system, right? So it results in something absolutely hilarious, which kind of fits the nature of the game. But, you know, ideally we'd have something better than this as well, so they wouldn't just be tumbling to their death. Here is another example from Skyrim, and Skyrim is, you know, pretty well known for its hilarious bugs in the AI. But this is sort of like a threat-aware pathfinding. So in this system, there's going to be this trap on the wall, and the trap is this thing on the wall here that when you walk into it, it's going to slam shut. And so what you'll see is that the enemies hear the player coming, and the interaction with the environment is pretty hilarious. So here the player is moving through the level.
Is someone there?
And then the NPC is like, is someone there? And then the player just hides. And this NPC who just saw that happen, the same thing is going to happen to them, right? So hopefully we could create a system that, I mean, but the thing is that sort of thing makes Skyrim. So you could call it dumb, but at the same thing, like, it's adding value to the game for me, right? All right, let's go to the next example. So here's some examples from the original StarCraft. Here's an example where we want to move all of these tanks to another location. However, the pathfinding system in StarCraft creates a single path, and then all of the tanks we control try and fight for position in that path. They all get stuck on each other, and then they all move single file. So by the time they get up here, if they've got some defenses up here, then they're just going to pick off these units one by one. And so that's not an ideal scenario for moving your units in a battle situation. Here, I've got another example where all of these SCVs, I'm telling them to attack this building. And so what they want to do ideally is surround the building as fast as possible so that as many of them can be attacking at the same time as possible. However, what you see, if this will work, is that they just get stuck on each other again, right? So they don't take that sort of initiative to go past it and surround, and so there's all these intricacies to pathfinding and the intent behind the pathfinding that make it sort of a difficult problem to solve. And in older games like StarCraft, the pathfinding can actually be hilariously bad in some situations. All right, let's get out of here. Slides, what are you doing? Come on. All right, here's an example from StarCraft 2 where the pathfinding system was dramatically upgraded. So here we've got like 200 Zerglings, and you can see them all moving as a swarm, right? Moving to the same location. And so the pathfinding in StarCraft 2 dramatically improved the quality of group pathfinding. And you can see they're all moving at the same time. They're squeezing together in certain areas. They're fanning apart once they reach their destination. It's pretty incredible how well the pathfinding works in this game. Next, here's sort of an example of like realistic behavior. And so these guys in the background here, this may not be the best example of pathfinding. They're trying to like get to some waypoint on the floor, but as they try and do so, you know, they're just constantly running back and forth and sort of interrupting the seriousness of this cutscene, if you will. So this is an example where, you know, you'd want to take the time to ideally fix a bug like this. This is from Dragon Age, I believe. Here's another example from the Fallout series, and this NPC is trying to get to my player's location. And the path it found was to run around literally the entire level before it got to me. So here is the NPC. It could have just run up like right here, taken like 2 steps up this ladder, but here's the path it ends up taking. Look at this. And who out there has seen something like this happen in a game, right? And you can sort of exploit the pathing in this way to like, you know, shoot an enemy and then have them run in one direction, then move slightly to the right, and then they take a different path, and then you shoot them again. And so here he is, finally makes it to the player after like a minute of pathfinding. That was unnecessary. Here's like one of these animation movement problems where no matter how, and this is a good a good use case for animation. No matter how good your system is, no matter how smart the pathfinding, if your animation ends up looking like this, people are going to think you're a little bit foolish, right? So animation matters, and if I move my camera out of the way, you can see that animation matters. So that was sort of the point of this slide. So now that we've seen some motivation for that, what is pathfinding? So video game maps are often filled with obstacles which NPCs and the player will collide with, right? Pathfinding is the name for the method that we will use to determine which path an NPC should take from its current location to a goal location. Pathfinding attempts to minimize a cost of the path. So the cost of the path could be the distance. So if you're trying to minimize the cost, and cost is distance, that is the least amount of distance, so the shortest path between 2 points. Maybe you're trying to minimize fuel. Maybe you're trying to minimize damage taken or some other arbitrary function. Pathfinding is trying to minimize some cost function from one point on the map to another point on the map. Excuse me. There are some considerations that we have to take before we just say, okay, pathfinding is important. What algorithm? Let's use this algorithm. Yes, let's use that algorithm. There's a bunch of properties of our pathfinding problem that we have to consider before we actually choose the algorithm. Because the properties of the problem define which algorithms are actually applicable and which type of cost functions that we can save. So, first of all, is it a single agent problem or a multi-agent problem? This means, like, is there only one thing moving or are there multiple things moving? Is there a single goal or are there multiple goals? So for example, maybe an NPC is trying to run toward a player, right? Or maybe the NPC is trying to run toward the nearest cover. So there might be multiple goals and they're trying to get to the closest one. Can your pathfinding be pre-computed? Is your environment completely static, right? Does it never change? If so, then maybe you could pre-compute paths. Or if your environment is changing or NPCs are moving around a lot, maybe you have a dynamic problem where you need to compute the path in real time or online. What is your space representation? So do you have like an open representation where sort of anything goes? Do you have a strict grid system that things can move on? Do you have a graph where things can move between nodes? Maybe you have polygons where like you can only move to the center of these polygons, etc. Also, you have to consider what movement directions you can take. Do you have like Zelda, up, down, left, and right? Do you have sort of arbitrary angles that you could move on? Maybe, again, you're just moving between nodes on a graph, like in something like Civilization, for example. You've got this hex grid that you're moving on. So let's have a look at that. So here's some examples of pathfinding. Oh, wow, look how blue my face is. It's crazy. The screen is the only thing lighting the room right now. I've got a pretty decent camera, so whenever the screen changes color, my face changes color. So pathfinding. Typically, we're in some environment when we're doing pathfinding, right? And we've got some type of terrain. So here we've got the blue terrain, for example. Whether that's water or not doesn't really matter. And we've got some obstacle here, which is green. So let's just pretend that we can't move through the green stuff, okay? So we've got two nodes or two states here in our environment, and we're trying to get from one place to another place. Typically, for a random single agent, single goal problem, which is the easiest type of problem that we could face, we're going to have a single start location. So the player is currently here, or the Goomba is currently here, or the Tech Knight is currently here, and they want to go over here. All right? So this is obvious, the use case for this. We want one NPC to go to one place, for example. Here's another case where we have multiple agents, single goal. That's a really interesting case. And this is used a lot in action RPG games. So if you ever played Diablo or Path of Exile, what you have is you have a player. The player would be the goal in that case. And you might have 3 zombies or something trying to get to the player. You might have 300 zombies trying to get to the player. If you ever played Path of Exile, you know just how many things can be on the screen. Or these might be homing missiles or some other entity that wants to get to the player. The point being that you could have multiple agents trying to get to a single goal. And if that's the case, maybe we have algorithms that could compute all of those paths at once, and we wouldn't have to do 3 separate pathfinding instances, for example. And we could also have single agent multi-goal. So that example that I talked about last time was, you have an NPC, maybe they're trying to get to the nearest cover, or maybe they're trying to get to the nearest health pack or something like that. All right, so those are the different types of pathfinding. Now we're going to talk about our space and action representation within our game. So the space and action representations, they're important decisions because the ideas are linked. Like how you represent your space is essentially how you're going to represent your actions as well. So which representation to choose is based on a bunch of stuff that comes from the game design, okay? And the choice of space representation in the pathfinding engine will determine which actions can be performed in the game, right? And also by the AI system. So just a couple of examples of space, state, and action representation. So maybe we have a system where we can do completely arbitrary fluid movement in any direction, right? And I'm showing you 2D examples here because it's easier for me to draw in 2D. But let's just say, I can move in these nice smooth curves at pixel level precision or even sub-pixel level precision. Maybe I have a game with just straight line movement. Maybe we're driving tanks around or something like that, right? And, it's hard for tanks to go on a smooth curve, so maybe you can only drive forward. Maybe we've got a grid system, and you can only move in 4 directions, right? So maybe we have a Zelda-like game. Or we can move in 8 directions. Or, instead of like a grid, we have a graph structure. And so maybe we have a graph with nodes, and you can only move between certain nodes on a graph. Another representation could be a polygon representation or a polygonal representation. So in this one, we could split up the environment into convex polygons. Convex meaning that there are no inward angles, okay? So any vertex can see any other vertex. Nothing will cut it off. So convex polygons are cool because one of the properties of a convex polygon is that any point in a convex polygon can see any other point in that same polygon, right? So anywhere within this rectangle, I know that I can move straight. There are not going to be any obstacles there. Any point within this polygon, the same thing holds true. And then what you could do is that, okay, well, if I'm trying to move from one polygon to within the same polygon, I know a straight line is possible. But if I'm trying to move from one polygon to another one, then I could say move to these junction points right between the polygons. So this is just an example of another possible way to represent your space. How do you choose that state representation? Well, it matters a lot, right? Because the memory size, first and foremost, depends on the representation. You may not be able to store information about every single pixel in your state representation, but maybe you could store this number of polygons, for example. Or maybe if you have a grid, then your grid needs to have a certain minimum or a certain maximum size because you can't store billions and billions of grid cells. So you've got to think about memory. And it also defines which actions are possible. And based on which actions are possible, it defines which algorithms are applicable to your space. So what you're trying to do when you go to make a pathfinding system or a movement system is you're trying to find a balance between the computation required to find the path, so talking about memory, talking about actions, talking about search time, versus the final path accuracy, right? Because if we have a more coarse representation, our path is going to be easier to find, but the final path is going to be less accurate, right? So there's always a trade-off between like the coarseness of our representation and the accuracy of our final solution. So typically in games, we choose a sparse state representation for easier computation. We do our computations in that sparser, more abstract space, and then later we can refine the path to look more realistic. And I'll talk about what that is in a couple of slides. Navigation meshes. Navigation meshes are cool. What if my game has sort of an arbitrary 3-dimensional or 2-dimensional geometry? Okay. Well, in that case, we're going to need some sort of structure. We can't just say, like, perform an algorithm on arbitrary floating point numbers because there's too many of them. So what we're going to do, well, we're not going to do this, but if we have a AAA game, typically one of the most well-known solutions is called a navigation mesh. And a navigation mesh is essentially a graph structure built out of polygons within our environment to enable pathfinding. The graph is called a nav mesh. Most game engines, like Unity, Unreal, they're going to come with some sort of software to build and edit a level's nav mesh. All right. And I may talk about more stuff about nav meshes later. So here's an example from a game engine. I believe this is an earlier version of Unity, where the player, the game creator, the programmer, whatever, is creating a navigation mesh for this particular level. So in this level here, you can see it's 3-dimensional. You've got two pillars over here. And what you can see is, at first, it's a little bit hard to see, like the animation is a little bit fast, but the player clicks create nav mesh, and then the whole area is traversable with this nav mesh. And then what the designer says is, okay, I kind of don't want the player to be able to rub right up against these pillars. Maybe they're dangerous, or maybe they're geometry I don't want the player to touch. So using this tool, it cuts out part of the nav mesh so that the player can no longer move there. Okay? Now, over here, it also cuts out 2 locations here that the player can't move in. But as you can see, it also adds a part to the nav mesh where the player can actually like vault over this wall in the middle. So wherever you have like vaulting in video games, like a special animation that you can do, that has probably been manually constructed by some game designer. Is that, oh, right here over this box, you're going to be able to vault over this thing. And they have put nav mesh there in order for that to be possible. Now, it's not necessarily the case that they've manually done that, but like maybe the object of the box or the wall or whatever has been told by the game engine to put some nav mesh there so that we can navigate between them. So here, I believe this is a video. Is this a video? I think so. 1 second. Why isn't it playing? No, it's not a video. The video's next. So right here, what we have is an example where we've got some strange geometry here. But in this world, you want the player to be able to sort of walk on a wall. Maybe you've got a spider character or something like that. So not only can you put the nav mesh on the ground, but you can also put the nav mesh on the wall, and you can create transitions that say, okay, we're allowing the player to walk from here to the wall and around these things. Okay, so you can see here that the designer has put some nav mesh on like the wide part of this obstacle, but not on the side of it. So you could move here, but maybe you can't move right here. Okay, and here's sort of what a final result may look like, where the programmer here has said, okay, the entire floor is filled with nav mesh, but you can't go really close. They don't want you to be able to like clip through this block. Now, in order to make these stairs, they've put nav mesh on each step, and they've said that, okay, there are transitions between these points. So they've included labels here in the nav mesh that say, okay, this node in the nav mesh, if you walk onto this point, it will jump you to this point in the nav mesh. And then they've defined some sort of animation on that as well. So we're not going to get, obviously, as in-depth with our game because we're in 2 dimensions, but I just wanted to show you how, like, in more complex settings, how this nav mesh is created and what it's used for. And so this will define the graph that you then would use for your search algorithm, whichever, or your pathfinding algorithm, whichever pathfinding that may be. So many graph search algorithms exist for pathfinding shortest paths. There's lots of them, each with their own properties. So very common, we may have something like breadth first search you could use if you have a very simple environment. You have like Dijkstra's algorithm, which I'm sure you've talked about in a previous algorithms course, or you could have the A-star algorithm. So most video game pathfinding has traditionally used some variant of the A-star algorithm. Now, if you want hours of lecturing about the A-star search algorithm, go to my YouTube channel, click on playlists, click on Computer Science 3200, and then click on the lectures for search and the A-star algorithm. I'm just going to give brief details of the A-star algorithm here, but if you're really interested in it, I have hours of lectures on algorithms like this for the other course, the Intro to AI course. So A-star is the most well-known best first search algorithm. It evaluates nodes by using 2 properties called G and N. So G is the path cost so far to the current node. Your heuristic function, f of n, is equal to g of n plus h of n, where g of n, that's a typo. H of n is an estimate of the distance between the current node and the goal node. So what we do is we have an open list that we add nodes to, similarly to breadth first search. We take out the node with the minimum f of n, and we have this algorithm, okay? So we have a function, we have a closed list, and an open list, which we implement as a priority queue, and then we loop until we have a solution or we have not found, until we've found a solution or until we haven't found a solution. And I'm not, like I said, I'm not going to go into the details of this here. I just wanted to have a slide on the A-star algorithm. And if you want to implement this for your project, please go watch the 3200 lectures on the A-star algorithm. I've got slides in here on the admissible heuristic, and I'm not going to go into details on that because that's all in the other lecture for the other course as well. But what I will do is show you this. So if I go to my website /search, which I will paste into the chat now for people who are live, I have this, and if you've taken 3200 with me, this probably, maybe you have PTSD over seeing this already, but this is a pathfinding demo where you can visualize the A-star search algorithm trying to find its way from a start node to a goal node. You can, and here if I let this run, it'll find the shortest path between the 2 nodes. You can change, well, once this is done, you can change the object size. So here, for example, if I have a 2x2 object or a 3x3 object, the paths are going to change there based on that. You can select different maps. So here we have a large maze-like map, and you can do the pathfinding there. There we go. There's the pathfinding. So this system lets you play around with different pathfinding algorithms and see which one might be correct for your game. Excuse me. All right, so that's there for you to play around with if you want to. But we're interested more in video game programming. So what is the workflow that you would do if you were trying, if your boss came over and said, we need a pathfinding system for the game? What would it actually look like for you, the programmer? So First, you'd identify the problem that you're solving, right? Is it single agent, multi-agent, single goal, multiple goal, whatever. You would construct a space representation that you think would fit well for that type of problem. You'd decide on which actions are possible in the game. You'd be given some sort of start and goal locations. You would apply an algorithm which finds a path from the start to the goal. And then you'd follow the path from the start to the goal. So let's look at an example of what that might look like in a game. So here we go. We're given, like, this is a level, for example, in a video game. Maybe we want to go from up here to down here, right? And this level has some sort of geometry. So let's choose a space representation. Let's say I have chosen polygons. Okay, so I've chosen polygons to represent my level. So what I do here is I choose polygons such that I know that any point from within one polygon can easily move in a straight line to within its own polygon, and possibly, ideally, neighboring polygons as well. Then what I do is I'm given some sort of start and goal location. So up here, maybe I have a starting location, which is the player, and I'm given a goal location down here. So I determine the starting node in my graph, my polygon graph or my nav mesh, and I've determined the end goal, and then I run some sort of pathfinding algorithm, right? The pathfinding algorithm says, okay, here are the nodes in your graph that you have to walk through. Then once I have that, what I'm going to do is going to refine that path a little bit and show the actual waypoints that the player should walk through in order to get from one point, from the starting point to the goal point. So that's essentially what's going to happen if you're creating a pathfinding system for your game. And then, of course, the last part is, now that I have the path, how do I actually follow that path, right? Because the following of the path turns out to be tricky in some situations as well. So now that we've computed the path, how do we make our agent traverse it, right? You've actually got to walk it. So the simplest way that I could think of, that I've seen, is just waypoints. So each point along the path is a waypoint. The path to the next waypoint is always clear. So you're going to define your waypoints such that you can always move in a straight line between your waypoints. You're going to walk one waypoint to the next waypoint in the line, and then you'll stop when the NPC reaches the goal or it's out of waypoints. So for example, let's say that I'm in a grid representation environment, and I've done 4-directional movement within the grid representation to find this path, right? So I want to get from this start to this goal. So what I did was every cell in my state representation, every grid cell, I put a waypoint. So essentially, when I walk, I'm going to go from this cell to this one, to this one, to this one, to this one, and then each waypoint along the way until I get to the goal. So that's pretty obvious. However, what if I didn't have so many waypoints? Because this is a lot of starting, and depending on the acceleration and deceleration in the game, if I like sprint a little and then stop, sprint a little and stop, sprint a little and stop, they may look really jerky. So maybe I do a little bit of path refinement, right? So what I could do, maybe I'll just delete every second waypoint, right? So now I'm going from here to here, to here, to here, to here, to here, to here. Can I keep going? Maybe what I should be doing is trying to get the fewest waypoints possible, such that all of these, like maybe I'll go through and eliminate all waypoints until a waypoint is no longer in line of sight. And so maybe I end up with something like this. Like all the waypoints from here along here, these are all in line of sight. This one wouldn't be. So I take the one before it and I just move in a straight line there. And so instead of following this path, now I'm following a much shorter path. And so this would work if I'm allowed to do like arbitrary movements and stuff like that. But now what I can do is refine the path even more, and maybe I want to follow this path in like a smooth curve. So maybe I have some sort of Bezier curve or steering or something that I'll show you a little bit later that makes this path really, really smooth. So what you've seen here is that I've taken a problem, I've chopped it up into a grid, right, which is a grid or a graph structure. I've refined my waypoints and then applied a little bit of smoothing. And so even though my pathfinding algorithm only moved in 4 directions, I've ended up with a really nice smooth path. Okay, so that's one way that you can take a more abstract state representation and turn it into a more fine-grained path from your start to your goal. Beyond the basic search algorithms that you've seen, you can use, I'm just going to name a couple of different ways that you could also do pathfinding. One of them is called vector fields. Sometimes they're also called flow fields or influence maps or vector maps. And they're a very efficient structure for pathfinding in cases where you want to go many paths to a single goal. Excuse me. Any case where multiple NPCs need to go to a single location, I would consider using a vector field. And I'll show you what a vector field now in a second. Must balance computation time with how many NPCs, etc. So, here's an example. Let's say we're playing something like Path of Exile, right? And we've got 100 NPCs coming after the player. In this example, we've got 10,000 NPCs going after the player. Now, in this case, how would we do this? Would we run A star 10,000 times? Right? We don't have time for that. So what we're going to do is this is using something called a vector field. So in a vector field, I'm just going to give the brief overview of this algorithm. If you want to actually implement this algorithm, go ahead. This is actually an assignment in my Computer Science 4303 class, is to implement exactly what you're seeing here on the screen. So step 1 is something called a distance map. In a distance map, let's say you wanted to get from this location to this goal location. Well, what you do is you start at the goal location and you breadth first search outwards and you record how many steps it took you to get to that location. So for example, we're going to breadth first search out from the goal and mark each of the locations that we hit with a 1 because it took 1 step so far. From each of these 1s, we're going to breadth first search out, mark them as 2s. Okay? So we do that. And then from each of the 2s, we go outward and we mark them as 3s. From each of the 3s, we mark as 4. And you can see essentially what we've done is for our whole grid, we've created a data structure which says how far is this grid cell from my goal location. And it does that for everything on the map. Then the second step is just, okay, for each cell on the map, let's say we take this one over here. Now that I know how far this is from the goal, how do I know how to get to the goal? Well, it's really easy because all you do is you look at all your neighboring cells and you go to the one with the lowest number. So you go from this 9 to this 7 to this 6, 6 to 5, 4, 3, 2, 1. Okay? And so this is literally the whole algorithm, and it's what you're doing to implement this sort of system. As I said, this is an assignment in my Game AI course, so if you're looking for a course in the winter and this sort of like really cool Game AI interests you, please take that course. We do this and we optimize it, and it's really fast and it's really cool. We can do hundreds of thousands of points. And so what you've seen here is we've done one algorithm that fills the whole screen, and now we can essentially do infinitely many paths to a single goal location because of how we've implemented this. So those last 4 slides came from this website. So I'll give you a second to hit print screen if you want to go type that in. It'll be in the slides for people who are in the course. Building on that sort of idea is the idea of an influence map. So influence maps typically incorporate other logic than just distance to goal. So for example, it could be used to come up... Let me save that for a second. Influence maps are used when it's difficult to come up with an objective function for other algorithms. So for example, let's say we wanted to avoid attacking enemies, or we wanted to keep our distance from attacking enemies, or distance from walls or lava or something, right? So it's very difficult to come up with an objective function for something like A star that says, give me the best path, but avoid this sort of thing, right? So here's what an influence map does. An influence map, let's say we have this starting location over here on the left, and we have this goal location, but we have an enemy here that we're trying to avoid, okay? So let's do the same thing that we did for the vector field. We're going to do this sort of distance map, right? However, what we can do now is we just avoid the enemy, right? We just don't let the player walk on the enemy tile. So if we want to strictly avoid the tile the enemy is on, that's a really easy thing. But let's say we wanted to avoid the coast of this island or something like that. Maybe we're in a boat and like it's shallow water and we might crash. So what we can do in an influence map is we have some value called an influence value. So what this is going to mean here, essentially, is that if we would rather go 10 extra distance than step on one of these tiles. Okay? So when we go to add up the distance map for the vector field, we just add 10 to all of these tiles. And what we get now is when we go to follow this path, right? Maybe we're going from the start to the 16 to the 15, but now we're avoiding this tile because it actually goes up rather than down, right? So I'd go 14, 13, and then come around like this, okay? What if we wanted to avoid the enemy even more? Maybe this enemy is like a turret with an attack range or something like that. So what you could do is you could have huge influence values here that really push you away from that enemy. So now when you add things up, you can no longer come down this way because the influence values are just getting so high, right? So this algorithm, it's not exactly as I've presented it on the map. I've simplified it a little bit just to show you how it would work. Because an influence map essentially is a repulsive force or an attractive force, either away from an undesired place or toward a desired place. All right. So that's what an influence map could be used for. Next, we're going to talk about steering behaviors. And steering behaviors are a part of your project, okay? So you will have to implement some sort of steering behavior on your project. So, steering can be seen as a framework for controlling autonomous agents, such as robots, CGI in movies, or NPCs in video games. Steering is going to add more realism and fluidity to agent movement, and it can really enhance the overall look and feel and experience of your game. And steering can be really cool and fun to implement. You can play with different parameters. You can see which effects can be produced, etc. And it's called steering because it's literally like steering in a car. Okay? So as a human, when I'm walking around, I can sort of turn on a dime. Like I can be walking in one direction and then just turn in place and move. But that looks really jerky when you have it in a video game. So what it is steering. You can think of it as steering in a car where you are altering slowly the path of a turn in order to get things to behave more more smoothly and more interestingly. So at its core, steering, like I said, is going to smooth the movement of entities in our games. Changing directions instantaneously or stopping on a dime can look really bad in video games. And so steering is going to act as a force that smoothly guides an entity toward a target. All right? I need to fix something on a slide. Just give me 1 second. All right. Okay. And so steering will be part of a project. And when I say that it's a force, picture you're moving your hand straight up. Okay? And I'm moving my hand straight up, but I come with a force and I push my hand to the left a little bit. And you can see how it alters that. That's exactly what a steering behavior is going to be. We can think of ourselves as moving in one direction, but a steering force is steering us into another direction. And the mathematics of it, even though it produces really, really nice results, the mathematics are actually pretty simple. And it uses all the concepts that we know about vectors, 2D vectors in games, which is pretty cool. So here's what a steering behavior is at its core. Our entity is going to have some current position and some current velocity. And if you remember, the velocity is just the change in position in x and y at each time step. So my entity here is this box, and it's moving up and to the right at a certain velocity. Something happens in the game, and now I want my entity to move toward this target. Okay? So maybe it was moving towards something that died, or the bonus is no longer there, or whatever reason. This target appears, maybe it's a big shiny gold coin, and I want that player or character or NPC or whatever to now move toward this target. So this dashed red line is the vector from my NPC or my entity to the target. And that is we're going to call that the desired direction, because the entity now desires to go toward the target, right? The path that is directly from the entity to the target, that is the desired target. So if we take a vector and we make it the same speed, right? Speed is the length or the magnitude of the vector. So if we take a vector with the same length as the blue vector, but point it toward the target, that is going to be our desired vector, okay? That is the vector we desire to go in. We want to go in that direction. So to calculate this desired vector, it's not very difficult. You would be able to do this pretty easily now, knowing what you know. In fact, you calculated a desired vector in assignment 2, right? Because you had to tell where the bullet was going to go. However, instead of steering the bullet, you just shot the bullet in a direction. So the desired vector, the dashed red line, is simply the target minus the position, right? So if we take our destination minus our source, that is the vector that points from one to the other. That is the entire dashed red line. Now what we want to do is we want to take that vector and normalize it so that it's length 1, right? The reason we want to normalize it is because we want to convert the length of this vector into the length of the vel vector. So if we take this vector and we normalize it, we talked about normalizing before, which is just dividing each of the components by its length, then we have now a length 1 red vector, and we take that length 1 red vector, and in order to get it to the same length as the blue vector, we just multiply it by the length of the blue vector. So it's just 3 operations. Target minus pos, normalize that value, then multiply it by the length of the blue vector. Super simple. So that's what we have now. We have the velocity, so vel, that's our current velocity. We have a desired velocity that we would like to get to, or a desired vector we would like to become. So let's compute the vector that would take our current trajectory and change it to the desired trajectory. Well, you know how to do that now, because it's just, again, this is our desired location, this is our destination, this is our source. So if we take desired and we subtract vel, we get this green line, right? That would take us from vel to desired. However, if we simply took vel and added this green vector, this is the steering vector, we're going to call it, then we would instantly turn on a dime to face that direction. And that's not what we want to do. We don't want to instantly go toward the desired, because that's not steering, that's not smoothing. We want to scale this vector by some amount, okay? So let's say we want to steer 10% towards our target on every frame, right? So we would steer smoothly 10% each time. Then we would scale this green line, or the dashed green line, by 10%. So we'd multiply it by 0.1. And when we scale this vector, that is sort of reducing the force of the steering, right? So we have this green vector, and so vel plus the green vector is the actual. So actual here, meaning the actual velocity that we will want to have on the next frame. So that's what we have. And if we want to calculate the actual vector, well, the math for that is also very simple. So to calculate the actual vector, which is the steered velocity, right? So we've gone from going in this direction, now we're going in this direction, which is slowly taking us toward the desired direction. We're going to choose a scale between 0 and 1, right? Here we've approximately chosen, I don't know, about a third. So this is about a third of that. When you implement this in practice, if you've got a game going at like 60 frames per second or more, then you want your steering force to be very low, like 0.1 or even less. So steering, this is the dashed green line, is going to be desired, which was the red line, which I don't have anymore. Let me see if I can bring that back. There we go. So steering is going to be desired minus vel. So the red one minus the blue one, that gives us the dashed green line. Then we take that dashed green line and we multiply it by the scale factor, which is between 0 and 1. And then once we have this smaller green vector, we're just going to add it to velocity. So then actual equals velocity plus steering. So all in all, here's how it goes, right? This is our whole situation up here. I know my camera is covering it, so let me move that a little bit. I don't think that'll get in the way. So here's our whole situation. We've got our target, we've got our current position, we got the desired vector, the current velocity, the steering force, and the actual vector. I know it's a lot of stuff, but it's simple once you get it. So you're given the current velocity, you're given the target, and you're given the scale. So desired equals target minus pause, right? That is the dashed red line. Then you're going to say desired equals desired minus desired dot length. So that gives you the unit or the normal vector, the unit vector here by normalizing it. You then multiply that one length desired vector by the length of the velocity vector to get a vector of the same length. Then you calculate the steering vector, which is this dashed green line, by saying desired minus velocity. Then you take steering and you scale it by multiplying it with a scale value between 0 and 1. And then you get the actual vector that you want to go in, like actually like add this x and y on your next frame of your game by taking your previous velocity and adding the steering vector. And that forces you in a specific direction. So types of steering. There are multiple types of steering as well. So all of our steering is going to involve an entity, an initial velocity, and a target. What we just described was a seeking behavior, okay? So seeking is essentially, if you think about it intuitively, it's turning toward the target, right? So you take where the target is and you slowly turn toward it. There's another behavior called a pursue behavior. And if you think about it, if you're trying to actually pursue somebody, you don't want to go where they are, you want to go where they'll be, right? So what you do is, instead of taking the position of the target as the desired vector, you take the target plus its target velocity, point to that, and then that's where you want to go, right? So if I'm going like this and I want to catch up, oh God, I can't really do this, then I'm trying to I'm not going toward here, I'm going toward here because I'm trying to catch up, right? That's what pursuing is. And you get this different type of behavior with steering just by changing the target location. Not only that, but you can also have a flee behavior. This is really cool. So you can avoid a target instead of going to a target just by flipping the desired vector. So the desired vector, instead of pointing to the target, it points away from the target. So instead of doing target minus pause, you do pause minus target. All the other math is the same, and now you're fleeing away from something. It's pretty cool. However, One of the issues with steering is that when we get close to the target, the entity is going to oscillate. Okay? It's going to oscillate real bad. It's going to like go back and forth, back and forth, back and forth. I'll actually show you an example of this. So what we're going to do is we're going to define an arrival behavior. And what that means is as we get closer and closer to the target, our behavior is going to change a little bit. And so, for example, the simplest thing you can do is to just scale the speed linearly as it approaches the targets within some distance. So it just means that you're moving at a certain speed as you're catching up to the target, but as you get really close, you're going to slow down, right? So think of it as like a parking spot. You're going to drive like, you're driving 60 down the road, and then you're going to turn into the parking lot, and you're not going to go 60 like right into the parking spot. Right? As you arrive at the parking spot, you're going to slow down a little bit. I know maybe some of you go, full send right into the parking spot, but think of it as a parking spot. You're trying to gradually ease yourself in there in order to not be too crazy. And for arrival behavior, there is no best value. All right? You just have to try it, and it's going to look different for every game that you have. So here is an example steering behavior. So in this game, we're just placing targets around the map. Let me move this. And as we place targets, the cute little kitty here is seeking toward that target. And you can see that the kitty is steering, right? It's sort of this smooth behavior. It's not just turning immediately to go in that direction. And that, in essence, is what steering is. It creates that sort of smooth turn toward your target. And that looks a lot more interesting than just immediately moving. Here is an example of avoidance steering. So let's say you're in a hockey game, right? You're trying to make a sports game, and you want your AI to avoid these things. So what you do is you have some target that you're trying to get to, but you can also put in repulsive steering forces from enemies so that instead of like going right up close to this enemy, you're going to steer away from them as you get to your destination. So that's an example of avoidance. Also, if you have like a bunch of agents, they can be steering and having attractive forces to their own color here. So if the blues are attracted to blues, the whites are attracted to whites, and they each have some sort of direction they're trying to go in. But they have repulsive forces toward other things so that they're doing like very basic obstacle avoidance, right? And there's a really cool steering system here called OpenSteer, and you can go to this website if you want. There's a really cool demo that you can download and look at. However, what I want to show you is something that I did really recently. So if you are doing 3200, I tried to change assignment 4 into something more cool. However, I didn't quite get there in time. So what I did do was this. If I can go back to the middle monitor, is I was trying to make a genetic algorithm control this like fish in a fish tank. Okay. Now I didn't quite get there in time, so you're stuck with this year's assignment, which is still the Sudoku solver. But essentially what's happening here is there's this little fish, right? This blue fish in a fish tank. It is trying to eat the food. And so all it does is it sets its current target to the closest green pellet and then steers toward that green pellet to eat the food. And whenever a green pellet is eaten, you get another green pellet, which is randomly spawned. Okay. Now, I didn't get this ready in time for this class, but it's also supposed to avoid the red pellets, but it doesn't always do that in time. But you can see this sort of like lifelike, cool behavior that you get almost for free just by implementing this little bit of steering code. What was it, like 6 lines of code? So it's pretty neat. And like this took me like 20 minutes to do. And so I'm sure you can do some really cool examples for your game for the project. So steering is in the project. So if you do attractive and repulsive steering, that is a form of pathfinding that you can use for your game, right? Maybe you are repulsed from tiles that you would bang into, but you're attracted to the player character, something like that. So just keep that in mind for when you're doing your project. Okie doke. That is the lecture for today. We got it done. I was zooming there. I was talking fast because I thought that was going to take a long time, but it ended up not, which is pretty neat. So that's as deep as I'm going to go into pathfinding and steering for that. But like I said, if you go to my website, you go to Teaching 3200, okay? So 3200 also has lectures on YouTube. And if you want to implement the A-star algorithm, then there's an entire lecture here where you can see more of my my beautiful face talking about the A-star algorithm and going through a huge example for almost 40 minutes explaining what the A-star algorithm is, what it does, and why it's cool. So that lecture is there for you if you want to go and implement A-star. Alrighty, next lecture, we're going to go into a cool topic, which is sort of game tools, because it turns out that tools are really great. And game tool programming is as important as game programming itself. And we're going to talk about specifically drag and drop. And part of the project, as we saw last time, was a level editor. And I will go through code with you in the next class to show you exactly how you can take our current game engine and implement drag and drop. I'm actually going to do it in the class, okay? So I'll do a large portion of your level editor for you, and it's so simple. It's just so simple that like you'll really appreciate ECS when you see how simple that is. Like we'll be able to drag things around in our level editor as the level is being played. Actually, let me see if I have that I can actually show you in real time. Give me a sec here. I may have it ready right now. I may not. I hope I have it ready. I wasn't planning on showing it, so I didn't have it. Give me one sec. Ah, crap. Let me try one more thing real quick. Oh, no, it's not here. I know where it is. One second. Apologies. Pin. Yes, okay. So here, if I go back to the main scene and I run this, so this is some code that's not part of the course, but it's something I've done on my own. So this is like a Mario level, right? You're very familiar with this scene now, but just watch this. This is what we're going to do in the next class. You can see here that we've got a little dot that's following around my mouse. So that's just a little debug thing. And I'm going to be able to click and pick up tiles in the level and move them around. Okay? And this is updating in real time as the physics are still happening in the level. Right? And it even like you can pick up the player, you can move the player around, drop them wherever you want. Oops. Drop them in a cliff. So this is pretty cool because you can see immediately you can say, oh wow, that's a level editor. Right? Instantaneously, that's a level editor. And the cool thing is, here's a game idea. You can do a really cool game. Like, for example, let's say the goal was to get up here in the level editor, or in the level, right? Maybe one of your game mechanics is, look, maybe I can, like, this is actually really hard to do, move the player around and, like, have this, like, maybe this is part of your game mechanic, is you get one tile that you have to, like, walk on. And, like, all this comes for free with, like, less than 10 minutes of coding. And all because of ECS. Okay? So, oh, look, I don't like that. Let's move it over here. Let's move a cloud. Let's move this guy. Get out of the way. All right. Anyway, you see what it is. That's what we'll be doing in the next lecture. So that's going to be pretty cool. Awesome. All right. So that is it for today. Thanks a lot for tuning in. And I hope you had fun learning about pathfinding and steering.